So in the previous video, we defined a free modules in a sort of abstract way using universal properties. And we're going to sort of see part of the utility of that in this video because we're finally talking about the proper, full, abstract definition of a tensor product of R modules. Again, to remind you, if you're not so comfortable with the concept of an R module, just pretend everything here is a real vector space. Of course, there are pitfalls about that because there are things that are true of vector spaces and tensor products of vector spaces that are not true for all R modules, but it's pretty safe, at least for going on some basic intuition. Now, before we really get down to the details, I just want to remind you that if you have any questions, you can leave them in the comments. Depending on how much time I have, maybe I'll be able to make a video response about your questions, or at the very least, just give some sort of rough explanation, point you to some sources or something like that. So do not be afraid to ask if there's anything that doesn't quite make sense, or that you would just like more details on. So the first thing I want to go over that's going to be useful is just to remind you for, say, if we do have a pair of real vector spaces and we have vectors, say, x having coordinates x1 up to xn and some other vector y having coordinates y1 up to yn. If you've studied some linear algebra, you've probably already realized, probably already learned about the dot product, which is a really useful tool for understanding things in linear algebra, where we just multiply the corresponding entries and add all the results together. So another notation for the dot product is to use this these little arrows on either side, because the dot product is a specific example of a more general thing known as an inner product. So let me just quickly remind you of a couple properties that the inner product satisfies. So let's say if we had vectors u, v, and w and some scalar alpha, if we had u plus alpha v w, then this is actually equal to u w plus alpha times v w. And the same thing happens in the second entry. If we had u and we had v plus alpha w, then this would work out to be u v inner product plus alpha times the inner product of u and w. So in other words, what this is saying, if you imagine for a moment, say in this first example, if we sort of ahead of time, if we pick some vector v and we think of v as being fixed, and then we think about being able to put any vectors u, v, and any scalar alpha in here, and you look at what is happening in this first component, what this is really telling us is that this defines a linear transformation. The map that sends a vector, say, x to x w, this defines a linear transformation from your vector space, your real vector space, into the real numbers. In other words, right, it's a linear transformation in the two coordinates. So it defines a linear transformation in these coordinates, and then conversely, we could have the operation that sends y into u y for some fixed u. So this defines then, because it defines a linear transformation in both coordinates, this is an example of what we call bi, meaning two, linear. So I just wanted to give that as a very important example of why one might even care about studying bilinear maps in the first place. Of course, now the question is, well, what does this have to do with tensor products? The thing is that what tensor products allow us to do is give us a new tool for studying bilinear maps. The thing is, of course, again, when we're thinking about arbitrary rings, things are more complicated. But when, at least if we have what's called the principal ideal domain, or again, we can just think about the case of vector spaces where we have a field, then we really understand linear maps well, right? I mean, it's a first year undergraduate course in mathematics. You spend a lot of time using it, and a lot of things in mathematics come back to using linear algebra in some way. So if there's some way that we can sort of re-understand bilinear maps in terms of linear maps, that would be pretty useful. So towards this definition of a tensor product in general, I said that we're going to do this in terms of a universal property. And let's start thinking about what that might look like. So a bilinear map, of course, takes in two components. So let's imagine we had an R module M and an R module N, and we're just thinking about their normal Cartesian product. Just as the inner product above is really a map from a Cartesian product into, say, the real numbers. And so we have this linear map we're going to call phi into some other R module P. Bilinear map, right? We've got this bilinear map. Okay, so we could redefine the map to somehow get something linear. And in a sense, that's what we're going to do. But one thing we could think about doing is, well, what if instead of, we have this bilinear map, we really understand linear maps, what if we sort of change the perspective of the space that we're working with? And that change in perspective changes the bilinearity into regular linearity. So this is essentially what the tensor product is going to be. So we're going to try and define this tensor product in terms of a universal property. So we say M tensored with N, and oftentimes we specify the ring that this is being tensored over. And we should want to turn our map phi down here into a map phi tilde, so that this map is R linear, no longer bilinear, right? Our map phi is bilinear. We want to turn this into an R linear map on our new object. And of course, we're defining a universal property, so we want this object to be uniquely defined if it exists. And so we should hope that this map then, that we can have a uniquely defined map satisfying this property. Now, the only thing left to consider is we need some sort of map between M cross N and M tensor N. There should be some sort of natural map, and so that we can say this diagram commutes. The question remaining is, well, what direction should this map go in? Either there's some sense in which M tensor N is bigger than M cross N, or it's smaller than M cross N. Now, if you sort of think about it, it's harder to sort of extend things to a larger space. But what we can imagine is that normally if we have a map that preserves some submodule, right? If there was some substructure of M cross N, and we know that L restricted, phi restricted to L was just the trivial map. Then from the universal property of quotients, which hopefully you've seen. If you've not, if you ask me in the comments, I can do a video about it. But then we know that this will induce a map on the quotient to P. So we should already be suspecting somewhere, maybe there's some way to turn this into a quotient. And in fact, what we're going to do to try and construct this thing is we're going to use, as promised, the notion of free modules from the previous video. So recalling that the free module sort of gave us we can work with this initial space without having to worry about any extraneous relations on it. What we're going to do is first pass to the free module and work with that. And then maybe we can quotient out the relations, the bilinear relations we want to be there. So we have our map phi as part of our input data. And what we get here is now by the, if you go back and you think about the diagram of the free module, we have this map J from the set M cross N into our free module. And recall that we had a concrete realization of the free module is just R direct sum M cross N, and this was just some sort of space of functions. Now, the universal property of the free module tells us that there is a unique R linear map, which I'm going to call phi hat down here, which makes this diagram commute. Okay, so now we've got a free module, and we want to somehow impose these relations to give ourselves ultimately an R-linear map into P from some sort of tensor product. Now, the key here is you might think that perhaps this already does the job, but remember, J is just some sort of set map. And so thinking about this diagram we have above, we would really like the arrow going down here into some sort of quotient where this is also a bilinear map. We've constructed part of this so far, but now what we're going to do is we're going to let K, this is going to be the submodule, so submodule of our free module, and we're specifically going to define it as being generated by certain relations. So basically, we're going to force the R bilinearity through these relations. So for example, if we take this map J, we want to say that for all R1 M1 plus R2 M2, and then we'll stick an N here. So this is for all R1, R2 in the ring, M1, M2 in M, and N in N. We're going to set this relation to be, it'll be this, subtract R1 times J, M1, N, minus R2, J, M2, N. And so if this thing were 0, right, if this whole expression here were 0, I mean, that would be one of the conditions we need for J to be a bilinear map, right? It's linear in one of the components, fixing the N. And we want to make sure this holds for all possible choices. So we're going to toss this. This is going to help generate the submodule. And we're also going to demand that the submodule, of course, is generated by linearity in the second component. So I'm not going to write that out. It's just the corresponding statement in the second component. So what that means then is if we quotient out by K, it means that those generators all become 0. In other words, that means that this term will be equal to the sum of these two terms in the quotient, which is exactly what we want. So now the only thing I want to check here is we're going to rely on the universal property of quotients. So we just need to make sure that our map phi is actually going to be 0 on L here. Well, in order to do this, we're going to use basically the things we already have. Now, in order to make sure that we get some sort of well-defined map induced on the quotient, we need to make use of this universal property of quotients as well. That is, now we're working with this new map that we've obtained because we're going to be taking a quotient of the free module. And so we want to make sure that this new map restricted to this generated submodule K is the identity. And then we'll be able to use the universal property of quotients. Towards that end, let's suppose that we had some arbitrary element of the K module. So that is, let's say that we had this J, R1, M1 plus R2, M2, N minus R1, J, M1, N minus R2, J, M2, N. And we want to make sure that our map phi bar is trivial on here. So we take phi bar of this whole entire thing. Now, from the universal property, we know that the map phi bar is an R-linear homomorphism. So we know that we'll be able to factor it through these sums, and we'll be able to pull all of the coefficients out. The other thing to notice, I guess I should scroll back up here, is the universal property tells us that these maps commute. So the result of applying phi bar of J to some element is simply the same as applying phi to some element. So if we carry all of that out, what we get down here, what you should find is that phi of R1, M1 plus R2, M2, N minus R1 phi of M1, N minus R2 phi of M2, N. But now, remember, our original map phi was assumed to be R bilinear. So that means that we know that this term here is equal to this term for all choices of R, M, and N, and therefore it's equal to 0. Of course, you still need to check that this condition holds on the second generator, but the proof is basically identical. And so I'm going to leave that to the audience to work out for themselves. So this basically concludes the proof that phi bar restricted to k is 0. And that tells us from the universal property of quotients that I now get a map. So if I consider my here pi is the projection map from the free module to the quotient of the free module by k. And the universal property now tells me that there exists a unique map commuting with this diagram, which I will call phi tilde. And this map, so now the only things left to check. So this we have our diagram, and I'm now going to tell you that our definition, this is going to be our tensor map. So if I scroll back up to the universal property that we wanted, by that I mean this is this map here, which is our bilinear. This object down here, this is our concrete model that we're going to take for the tensor product of M and N. And of course, this is the supposed bilinear, the R-linear map that we want to take from here. And the rest of it is a matter of simply composing these definitions together. So for now, I think I'm going to leave just the, double checking that phi tilde, is in fact R-linear from this module. Oh, actually, we do know it is R-linear by the universal property of quotients. I suppose the one thing you might want to convince yourself of is that this map truly is R bilinear, but that is precisely handled by the quotient. If anyone gets stuck working that out for themselves, let me know. So finally, I just want to go back. We've done a lot of abstract nonsense to define this. So I do want to go back and just mention that, again, you should check out Michael Penn's video for the better intuition on these tensor products. But this does recover, say, if we had a real vector space V with a basis E1, E2, and E3, and say we had a vector space W with a basis F1 and F2, then the basis of V tensored with W over R would be E1 tensor F1 E2, E2 tensor F2, and so on and so forth, right? So in general, it'd just be the EI tensor the FJ. This would form a basis. In total, you would have 6 elements. So the tensor product is multiplicative in dimension. But the thing to be careful of here is this does not mean that all elements of the tensor product are of the form U tensor V. This is not the case. Tensors that do satisfy this, we call these pure tensors. But you have to be careful because you can't always argue just on the pure tensors. For example, you could have something like 2E1 cross F1 plus E2 cross F2. This term cannot be reduced any further into a simple tensor expression. Okay, so that is it though for this video. You've now seen the full, proper, rigorous, general way to define tensor products of R modules in terms of a universal property, and how to give it a concrete realization. But what I think people are more interested in now, Michael Penn's video gives a great, more, sort of hands-on approach to this. But what I want to start getting into in the next video is, how do tensors come up in physics? And for that, we're going to have to start diving into a bit of manifold theory and differential geometry.